Hello students, welcome back to the next lecture on classical electrodynamics, and today's class is lecture number 22. In the last two classes we have discussed a little more detail on understanding the Maxwell's equations, and we have also seen something on the gauge transformation and Coulomb gauge. Especially we have seen the Coulomb gauge with reference to static field, that means the static electric field and static magnetic field case. And the reason why such a kind of gauge is very useful is discussed in that class. I think it was lecture number 20, so you'll have to verify that. So ultimately, what is the purpose of having gauge transformation, and what is the purpose of having a gauge called Coulomb gauge? The ultimate reason is that the differential equation corresponding to the potential will be simplified. If you don't fix any gauge, then the differential equation corresponding to the potential will be fairly complicated, for which we do not have a solution methodology, which means analytical techniques are not known to solve that equation. Ultimately, we can always solve it by numerical technique, but however, learning the analytical technique, that means getting the closed form solution to the differential equation, is of highest interest, or it's of great interest, and therefore we first give preference to getting the solution in terms of analytical functions, that is called a closed form solution. When that kind of methodology fails, then we ultimately move on to the numerical method. That means the solution will be in the form of numbers, okay, as a function of independent variables. So the reason is clear, right? So why do you want to have a gauge? The reason is that the differential equation for the potential has to be as simple as possible, so that you know how to solve it by some standard method. That is the reason. But these discussions we have made only with reference to the static fields. So today what we are going to do is we are going to discuss a similar kind of situation corresponding to the dynamic field. That means you can consider both electric and magnetic fields that are time varying, and in which case we would like to know what would be the differential equations corresponding to the potential. So the potential formulation, this is what is known as the potential formulation, as I already pointed out in some of the previous classes. Potential formulation means rewriting the Maxwell's equation in terms of potentials. You have two fields, right? Electric field, magnetic field. Corresponding to two fields, you have two potentials. One is electric potential, another is the magnetic potential. And magnetic potential happens to be a vector, and therefore we typically say it is a vector magnetic potential. So whether you are going to use the differential equation for the fields, or whether you are going to use the differential equation for the potentials, it's all the different ways of approaching the same problem. We consider that dealing with the potential is little more comfortable than directly dealing with the field. The reason being that the potentials have certain kind of arbitrariness or freedom. So we can exploit the freedom in order to calculate the potential in a simplified manner. And once we finish the calculation of the potential, we can always obtain the fields. So that is the approach. We don't want to directly deal with the fields, but instead we would like to deal with potentials, so that we can exploit or we can make use of the freedom available for the calculation of the potentials. So this freedom is what is known as gauge. Okay, that's all about it. So the primary purpose is clear for you, and since we have completed the or since we have discussed the uh, Coulomb gauge corresponding to the static fields, today we would like to discuss the similar situation corresponding to the dynamic fields. And of course, the starting point is shown here. You can see that the Maxwell's equations are written here, and we are going to follow this number, and therefore the equation numbers are also shown here. The first equation and the second equations are homogeneous differential equations. That is why we have written the very beginning. Of course, it is this kind of numbering is exactly following the previous class. So you just complete the last class lecture and then follow today's work, so that the equation number will be maintained. So equation number 1 and 2 are homogeneous differential equations, and therefore they are reasonably simpler to solve when compared to the inhomogeneous equations, which are equation number 3 and 4. So that is why 1 and 2 is kept as the homogeneous case, and the last 2 is kept as the inhomogeneous. So within the inhomogeneous, the third equation is somewhat easier, and the most complicated equation is written down at the end. So that is how it is arranged. So the starting point would be to consider equation number 1 and 2, which are the homogeneous differential equation, and our primary aim is that we would like to eliminate the field. Eliminating means this B vector we would like to eliminate and bring the corresponding potential. So what is the potential? Capital A vector, what is known as the vector magnetic potential. So you eliminate the B vector and bring the A vector. And similarly, when you come to the electric field, you remove the E vector and bring the electric potential V. Okay, we can use phi or we can use V, and I think we can use any of them, and today we will use, for example, phi. Okay, so electric potential we are going to bring in favor of the field. So the ultimate idea is clear, right? In all these four differential equations, namely the Maxwell's equation, we would like to eliminate, that means nowhere field will be there. Instead of that, all equations will be having only potentials. If you bring the set of equations like that, then we say that we have understood, or we are trying to understand electromagnetism using the electromagnetic potentials. And this is exactly what is known as potential formulation in electrodynamics. That is the story. But then ultimately what happens is the differential equation corresponding to the potential will be fairly complicated, and then we would like to know whether we can exercise the freedom. Freedom means fixing some value of the potential, and interestingly that works. And if you are going to choose certain quantity to be equal to 0, then the differential equation corresponding to the potential also becomes reasonably simple, and therefore we are happy to solve those equations. And ultimately we are going to see in today's class that the differential equation corresponding to the potentials are nothing but the wave equations. And of course wave equation means you already know the solution. There are solution methods available, so you can always find out the uh, equation for the wave corresponding to the differential equation for the potentials. So that is the idea. So ultimate idea is that all the four equations, namely this Maxwell equation, will be replaced by only wave equations. So that is what is going to happen. So let us see how it all takes place. Okay, so let me therefore go to the board, and then we will start with, I will write down, first of all I will write down that the equation number 1 and equation number 2 are the homogeneous differential equation. That's what I am trying to write here, as you can see. And then the next 3 and 4 are going to be in homogeneous case. And then let me therefore show to the, I'll remove this and go to it, go to the board and then explain. Okay, so the reason I have already explained why we are considering the first two equations, they are reasonably easier to deal with. Okay, and so let us extract some additional information from this homogeneous equation. First of all, we will extract some additional information, and then we will move ahead to the equation number 3 and 4. So, okay, what information can you extract? So let me write down the divergence of B equal to 0, and this means that the B vector can be written down as curl of the vector. Of course, these things are discussed earlier, that's why I am quickly writing. And similarly, when you are considering the second equation, namely the curl of the electric field is minus dou B by dou T, then what we can do is we can substitute this value for the B vector. Del cross E, right? So you are taking the information from the divergence of B. What information means? You see what I am trying to say. We are going to extract the information. So what information is extracted, you see, because divergence of the magnetic field is equal to 0, the information extracted is that the magnetic field can be written as curl of something, and that something is what we call magnetic vector potential. So this is the information we have extracted, and that information we are going to transmit, or we are going to transfer to equation number 2, which is the Faraday's law. Now how do you transfer? Means there is a dou B by dou T is there. So in place of this magnetic field, you put the del cross A. And that's what I'm going to substitute. Okay, let me substitute and see what is happening. I'll be getting curl of A equal to minus dou by dou T of curl of A vector. So now you take it to the left hand side because both sides are curl, right? So therefore, since both sides you have the curl, you can take the to the left side. So I can take the curl of open bracket and then say E vector, then bring it to the left side. I'll get a plus. Then you get a dou A by dou T. Then that much is equal to 0. So of course you have a curl of something equal to 0. So whenever you see curl of something equal to 0, you should always remember what vector calculus says. Whenever curl of some particular vector is 0, then that kind of statement should come to your mind. And so I'll write down what is the statement. If curl of some vector is 0, then that particular vector can be written as the gradient of a scalar. So this is the standard thing which you are quite familiar now, and we will make use of this particular information, and therefore electric field plus dou A by dou T, that quantity can be written down as gradient of something. Minus is optional. I'll now write down the minus, which is completely what you call the convention. So this particular statement is therefore clear. It is the curl of something. So here you have a V vector. V is any vector, for example. So that V is actually E plus dou A by dou T. So therefore, this particular V vector can be written down as gradient of some other scalar quantity. And why do you want to put a minus is purely because of the convention. And what convention we have in electrostatics is that the electric potential will go to 0 at infinity. So this is by definition. We have a defining expression for electric potential, right? The electric potential is 0 at infinity. And therefore anything that you are going to evaluate is with reference to that. So because of that reason, you get a minus sign here, which is of course explained in previous lectures. And this is the reason why we are using a minus. So because of the minus, this equation will not be disturbed. Okay, ultimately you are going to 0, right? Whether it is plus 0 or minus 0, it's all same. So therefore this minus will not affect. And therefore what happens is that let us write down the electric field. You take this dou A by dou T to the right side, then I'll be getting minus dou A by dou T. So ultimately what happened is we are now able to get some kind of equation where you are going to eliminate the field. So why I am highlighting here? So you must be able to understand why we are highlighting, or we are saying that we are putting a box and saying that we got some conclusion. What conclusion is obtained here is that this is left side is field, electric field. Right side you don't have field. This is electric potential and that is magnetic potential. Every time you don't have to say magnetic vector potential. Okay. Initial time we say that it is vector magnetic potential because the story is quite different from electric case, because we are always familiar with the electric potential, which is scalar, and we are also quite familiar with the gravitational potential in mechanics, and that's also a scalar. So we have been dealing scalar potential for a long time, and even in thermodynamic potentials are scalar quantities. Okay, so because the magnetic potential happens to be vector, we have been emphasizing a little bit by saying vector magnetic potential. But once you understand that this is a vector quantity, we can simply say that it is magnetic potential. It's sufficient. So if that is the case, now what is the left hand side is you have a field, and in the right hand side everything is potential. And as you can see that electric field cannot be described only by electric potential. So this is important conclusion. So what is the conclusion? See, electric field cannot be understood only from electric potential. That is the meaning of this. In addition to that, you also need magnetic potential. So therefore, you can now see how the electric field and magnetic fields are connected. Okay, so the description of the electric field will be incomplete if you don't have any information about magnetic potential. And therefore electromagnetism is some kind of combination. You can't remove one field from the other. The two fields will always go together. So that information is now visible from this equation. So this has to be contrasted to, or you have to compare this particular equation to the well-known equation in electrostatics. Okay, so what is the well-known equation in electrostatics? Electric field is given by the negative gradient of the scalar potential, and that's it. Only the second term was not there. So in the case of the static field, the second term was not there. That is quite trivial, right? When you have a static field, the time derivative is 0. Therefore, second term you delete. So E equal to minus grad phi. So in the pure static case, the electric field can be described by electric potential. So that's fine. But when you are coming to the dynamic fields, where the electric field and magnetic field are time dependent, in that situation, you cannot describe by a single potential. You need a combination of both electric and magnetic potential. This is the important conclusion. And therefore, ultimately, our conclusion is that we are able to eliminate the field, and we are going to bring potentials in favor of fields. So that is the conclusion. That's why we have put a box or highlighting here. So therefore, here the point to be noted is that they are all field time dependent. So explicitly I am writing that. Everywhere you write down r comma t. That's what I am doing. That is equal to minus dou a of r comma t divided by dou t. So these two equations are same. Only difference is that electric field is a function of r comma t. That is space and time. R means space, t means time. So electric field is a function of space and time. The electric potential is also a function of space and time, and magnetic potential is also a function of space and time. We are explicitly writing here. You don't have to write every time, but at least for once, okay, at least one time you have to write down, so that you will realize and remember that each one of them is a function of x comma y comma z comma t. So that is very important. And when you are going to write like this, there is an important point to be noted. We will not call phi as an electrostatic potential. So the terminology should be very important. We will use electric potential. So that is the name. Electric potential is different from electrostatic potential. Electrostatic potential means the second term is not there, 0. That is static field. Electric potential means dynamic field. So that distinction should be very important, and therefore use the name electric potential for the phi now. So that is another point in terms of terminology. And this kind of writing is, of course, the main purpose is to remember that everything is function of time. And therefore now we are having, no, only phi is not there. So let me combination I have to write down phi comma a. That combination is what we call the electromagnetic potential. So you are also you are unable to discuss in terms of single potential, right? That is why a pair comes into picture, and this pair is what is known as the electromagnetic potential. And of course, as I already told you, this is not electrostatic potential. So whatever I explained, I would like to write down so that it will be easy for you to make notes. And that's all about it. This is the main information that we get from the homogeneous differential equation. So I will write down the conclusion. What is the conclusion I am trying to say is that equation 1, 2 are homogeneous differential equation. So what is your conclusion from homogeneous differential equation? That is a conclusion. So we are going to write that. So one is that the B equal to curl of A. That is one conclusion. And second conclusion is electric field equal to minus gradient of phi minus dou A by dou T. And that's it. This is the conclusion from the homogeneous Maxwell's equations. And so what is the meaning? The meaning is that we are able to remove the field. So I'll write down the meaning. The meaning is that electric field and magnetic fields can be replaced by the corresponding potentials phi and A. Okay, once again, what is the meaning? Once again, that is the Maxwell's equations can be rewritten in terms of phi and A. That is our ultimate aim. We are going to remove the field and bring the potential. And this kind of job that we are doing is exactly known as the potential formulation. So this is the potential formulation in electrodynamics. So of course, as I already explained, what is an advantage of potential formulation? That also I will write down. In fact, all of them are explained already. So what is the advantage of the potential formulation? As I already told you that you have some freedom and the number of components are lesser, and let us see that electric field and magnetic field means 3 plus 3 components. Three component for electric field, three components of magnetic field. For potential, it is not like that. One component, and then A vector will have three components, isn't it? So you have electric field means three components, magnetic field three components, that is the XYZ components. And in the case of the potential, you have only one component because scalar, and this is anyway a vector, so three will be there. So therefore, if you are going to make a total, how many components that you are having, it is quite easy to say that we are going to have 6 here and 4 there. So that means, so what is the important understanding is that if you want to deal with the mathematics of electric field and magnetic field, you are ultimately dealing with mathematics, right? If you are going to do an experiment, all these things are not required. We are trying to understand the physics in terms of mathematics. So if you want to deal with the mathematics of electromagnetic fields, then you'll have to work with 6 components of the differential equation. You'll have one differential equation for one component, so you have to deal with the 6 of them. But if you are going to have potential formulation, because this is a scalar quantity, this becomes 1, but anyway here 3 is there, but anyway 3 plus 1 becomes 4. So that means I am able to reduce two differential equations. That is one thing. This is one advantage, okay? And this is one advantage. The second advantage is that in addition to this kind of reduction in the number of components, we also have the freedom in fixing the potential. So there are two advantages are there. One is that the number of components that you are going to deal with is less than what you are going to have field. This is one advantage. The second advantage is potentials admit freedom. We have been discussing that in the gauge transformation. So you have some kind of freedom that you can exercise. But if you are going to deal with field, there is no freedom. You'll have to directly evaluate the integrals or whatever that you have in Maxwell's equation. You don't have anything freedom there, and therefore you have reasonable, valid reasons are there why we are dealing with the potential formulation in electrodynamics. So that's the reason. So once you understand that, okay, we have made the conclusion about 1 and 2, let us go back to the two more equations. Okay, we have conclusion made from homogeneous, right? Let us go to the inhomogeneous differential equation, and then we will see what can be done. Okay, keep this equation. Okay, I'll move on to the another place. Okay, so now what we are doing is that this conclusion is what we have obtained right now. The conclusion is from equation 1 and 2, and equation 1 and 2 are nothing but the homogeneous Maxwell's equation. So we have extracted all the information from the homogeneous Maxwell equation and brought it here, and that's the box here. And what is left out of the 4 Maxwell equation, 2 of them is job is over. Remaining 2 equations are there. They are the inhomogeneous Maxwell's equations, and therefore we will have to deal with the inhomogeneous differential equation. Okay, so which is the let us start with the first equation, what is known as the Gauss law. So what is the first inhomogeneous equation? Divergence of E equal to rho by epsilon naught. So that equation you take, and then let us bring this expression and substitute. So divergence of electric field is how much? Electric field is minus gradient of phi, then minus dou A by dou T. So I'm going to replace electric field equal to you have the rho by epsilon naught. Okay, and that is equal to, I think this minus, the right side is not minus, right? What is the Gauss law? Divergence of E equal to rho by epsilon naught, right? That there is no minus, this should be plus there. Okay, that is a plus, and therefore this is also plus. Okay, so therefore now let us simplify. So you get a del square phi, and then you get a plus you take the second the time derivative, then take the minus to the right hand side, I get a minus rho by epsilon naught. So as you can see, why did we put a box here is that we have made some conclusion here, in the sense that this particular equation, namely the inhomogeneous Maxwell's equation, has been now rewritten. In what way it is rewritten is that electric field has completely disappeared into this equation. Instead of the electric field, you have the potentials only. Therefore, what happens is that once again, from the inhomogeneous Maxwell equation, all the field is removed, and in place of that, we get potentials, and that is what we say in favor of. Okay, we are going to bring the potentials in favor of. In favor of means we are going to eliminate the field. But only disadvantage, of course, you have written the equation number, that's fine. But if you compare the Gauss law and then this particular equation, it is very clear that the divergence of E equal to rho by epsilon naught appears to be reasonably simple equation. But when compared to the equation number 6, so equation number 6, you see, it looks a little complicated. So solving this kind of equation is little more complicated. So what you understand is that the differential equation corresponding to the potential, this is the differential equation corresponding to the potential, equation number 6. This is differential equation, right? So differential equation for the potential is going to be more complicated than what you expected. So we thought that there is an advantage in doing the potential formulation, but ultimately what happens is that the differential equations are going to be reasonably complicated. But interestingly, what happens is, there is a freedom, given by the potential, and therefore you have the opportunity, or you have the exercise of making the divergence of A equal to 0. You have that option. Nothing goes wrong by setting divergence of A equal to 0. And therefore what happens is, when you set this particular thing to 0, and what you'll get del square phi equal to rho by epsilon naught, which is nothing but the Poisson equation, isn't it? So when the divergence of A equal to 0, which means that you are going to make use of the Coulomb gauge, then the differential equation for the potential comes down to the Poisson equation, and for the Poisson equation you have the solution methodology, and therefore you are again happy. So therefore this is how initially it looks as if it is a little complicated, but ultimately what happens is that we are going to make use of some gauge. So this is the story about the equation number 3, that is the first inhomogeneous equation in the Maxwell's set. Okay, that's over. Then what will happen is, we will next deal with the another that is the last equation, which is inhomogeneous. Let us go to that. So let me therefore write down the statement here. This is equivalent to 2. So I would like to write down that whatever we have written till now is nothing but it is equivalent to the inhomogeneous equation number 3. So the equation number 3 that I am writing here is the inhomogeneous differential equation, that is the Maxwell equation number 3. I am talking about Maxwell equation number 3. Okay. So once that is clear, now we will come back to the last equation. So what is the last equation? You have the so-called Maxwell's correction, right? That is known as the Maxwell Lampard equation. So the last equation is the one that is remaining. So let us write down that equation. You know the equation, right? Curl of the magnetic field is equal to mu naught into the current density, plus you have the Maxwell's correction. The last term is known as the Maxwell's correction, mu naught epsilon naught into dou E by dou T. And you know what to do. Okay, what all we have to do is that we would like to eliminate the field. So let us eliminate the field by putting del cross A here, and equal to mu naught into the source term J, plus mu naught epsilon naught into once again, you see, electric field can be written down as negative gradient of phi minus dou A by dou T. And so you can easily see how nicely it is we are able to eliminate the field. This magnetic field has disappeared, potential has come here, electric field has disappeared, you got the potential. And of course this is the source term that you have, the charge density and the current density, they are the source terms that will be there. And what is interesting about this particular equation, of course, that we are going to do is that if you are going to substitute the numerical values for mu naught and epsilon naught, you already know that 4 pi into 10 to the power of minus 7 Henry per meter for the mu naught, and something like 8.85 10 to the power minus 12 farad per meter for epsilon naught. You multiply them, and then what happens, you see, you already know what it is, but I would like to write down that the quantity mu naught into epsilon naught exactly happens to be 1 over c square. Okay, numerically, I'm talking about numerically as well as as well as in terms of dimensions. Ultimate product, you have the product, right? Ampere, what is this mu naught? Mu naught is Henry per meter. Epsilon naught is Farad per meter. You'll have to simplify, you simplify in terms of the fundamental SI unit, and ultimately what happens is the dimension is nothing but the 1 divided by of the square of the meter per second. It's quite easy to prove. Okay, you only have to simplify the dimensions. And this is not one thing that some of the students get confused is whenever c comes, c is what? Speed of light, right? Whenever c comes, some students have the opinion that it is the cgs unit. Whenever c comes, c is the speed of light. Whenever c comes into picture, some students think that the equation is written in the cgs system of units. It is not so. In cgs system of units, you will be getting the speed of light somewhere. Okay, in the Maxwell's equation, the speed of the light will be scattered somewhere, that is there. But however, right now what we are doing, this kind of mu naught epsilon naught equal to 1 over c square has nothing to do with the cgs unit. So right now this equation is completely SI units only. So that point you make sure. And what is that we are going to do is that this mu naught epsilon naught that is there here will be deleted, and then we will bring the 1 over c square here. That is the reason. And remember, just because c appears here, this equation is not in the cgs system. That is very important. This equation is still in the SI system of units. Okay, keep that in point. And let me therefore bring 1 over c square here and then rewrite this equation. So that is equal to, let us apply the the product rule. It is the gradient of the divergence minus the Laplacian. So that is the curl of curl. So that's over. Then that will be equal to, and plus, I think there is a minus there. So let me bring it to the left side. Plus 1 by c square. You see, the two minuses are there. So I am going to bring it to the left hand side. So if you are going to bring it to the left hand side, both of them will become plus. That is why I put a plus here. Then you have a mu naught epsilon naught is being 1 over c square. Then entire thing you simply copy here. So this one I will copy and I will be writing plus everywhere. So write down everything in positive, and that's all. What is left out on the right hand side is only the mu naught into j. So this is how the equation for the potential looks like. And of course, now as you can see that the entire equation contains only the potentials and all the fields have disappeared. And let us make a small rearrangement. I am just going to multiply by minus 1. Okay, multiply the entire equation by minus 1. So that's all I am going to do. So simply multiply by minus 1. So minus of the first term, then plus, close the bracket. Okay, plus of the second term, then minus of the third term, and of course they are here. Yeah, so here when I am taking dou by dou t inside, you have the freedom of interchanging the del operator and the dou by dou t operator. You have the freedom because one is time and the other one is space. Okay, space and the time are independent of each other. So whenever independent quantities are operated, you can operate in any order. So that is the reason. And therefore we have taken the time derivative first, and then later we will do the space derivative. That is the meaning. And the last term there is no trouble. Of course both of them are time derivative, so it becomes a second order. So now it becomes minus is there because we are multiplying by minus 1, and ultimately right side is also minus 1. So the advantage is that we are able to take something common here. So why did I multiply by minus 1 common is that you have two terms containing gradient. You see, this is a gradient term, gradient of dou phi by dou t. Similarly, here also you see this is gradient of something. So two gradients are there, right? So I will take a gradient common. So minus gradient of, open a big bracket, and then write down the two terms. First term is the divergence of A, and the second term, since minus is taken outside, I'll write a plus, and then I get dou phi by dou t because gradient has gone outside. So I am putting tick here. So these are the terms that we have clubbed together, and then what is left out finally? then what is left out is that I have del square A, then you have minus 1 over c square dou square A by dou t square, that equal to the minus of the mu naught into J. And that's it. There is nothing more to simplify. I will say that this is the final equation corresponding to the Ampere Maxwell equation. So you have the last inhomogeneous equation, right? Maxwell equation that has been completely rewritten now. That's what I'm saying. This equation is equivalent to the Ampere Maxwell equation number 4. This number 4 is actually Maxwell equation number 4. So you see that. So what do you feel when you look at equation number 7? Equation number 7 is looking so big, and remember, this is the partial differential equation. This is a partial differential equation. It is a second order differential equation, right? Second order in time, second order in space. So, so when you compare this equation with the Maxwell equation itself, this equation is certainly more complicated than the Ampere's equation. Ampere Maxwell equation has only curl of B. Curl of B equal to mu naught into J, right? That's all. So now this particular equation has become much more complicated. So, and therefore now we are going to think a little bit. Is this equation anyway? You don't have any solution methodology, and therefore you are now asking the question: can we exercise the freedom given by the potential and make some quantity 0? As you already know that the Coulomb gauge means divergence of A equal to 0. That is a Coulomb gauge. But however, if I put a divergence of A equal to 0, okay, this term goes to 0, but still you have this particular term extra. So the equation, gradient of this quantity, then plus all these things equal to minus mu naught into J. That equation is still much complicated differential equation for which you do not have the analytical solution. So therefore what happens is, making use of the Coulomb gauge in this equation doesn't work. So therefore we would like to understand what is this the second term that you have. I have written in 2 brackets here. The second bracket, this particular bracket you consider. Do you have any idea about what is this kind of equation? Have you seen this equation anywhere? There's a question, and of course this is the equation that is quite familiar to you, which everyone studies in acoustics, or we say waves and oscillation, whatever you call. Okay, so I'll show that what is that equation. So this is something that is quite familiar to you, what is known as the wave equation. You study in waves and oscillation. So the standard simple wave that you are going to consider will look like this. The partial differential equation corresponding to one-dimensional wave will look like this. So how it looking like? You have the second derivative in space is equal to 1 divided by velocity square multiplied by second derivative in time. So this is how the appearance is there. So appearance, remember, second derivative in time is there on side, second derivative in space is there in another side. And wherever you have the time derivative, there you have the 1 divided by velocity square. So this particular equation is known as wave equation. Why it is known as wave equation is because if you solve this differential equation, of course, that is this interesting point. We have the method to solve this differential equation, and if you solve the differential equation, we have the solution, which is given by some kind of sine of kx, whether it is sine or cos, it's okay. Kx minus omega t, some phi. I mean, you can have any phi, so arbitrarily you can have, and then the solution can be plotted like this. So this is known as a wave equation because the solution is a wave here, and this is the situation for one dimension. That means only x direction is there. If you are going to simultaneously deal with the x direction, y direction and z direction, then what will happen is that you will be having dou square u by dou x square, correspondingly y square, correspondingly z square. You will be having 3 terms corresponding to the x, y, z. Then what is that known as? Dou square u by dou x square plus dou square u by dou y square. Like that, if you add, that quantity is what is known as the Laplacian. So Laplacian, when it is appearing on the left hand side, that means it is 3-dimensional wave equation. The right side will be same. Time will not be, only one t is there. 3-dimension means 3 time will not be there. So that is only 1 here. So once you understand this kind of an appearance, now we will come back to our original place, and here you see you have the del square operator, therefore Laplacian is there. and then you have 1 divided by velocity square, and here you have the second order time derivative. Only thing is that this is a vector quantity, that was a scalar quantity, because one direction. If you are going to consider in all three components, then you will be having a vector quantity. So it is very clear that this particular thing represents the three-dimensional wave equation. You can always write down this particular equation as three separate equation, one for each component. And therefore the second bracket, that is this entire expression, is the differential equation that is quite familiar to you, namely the wave equation, for which we have the solution methodology. And therefore we are quite happy about this particular term. There is no trouble. So the trouble actually comes from the first term, for which we do not have uh, any analytical method that solves the differential equation. So we will have to exercise the freedom now, and the Coulomb gauge itself is making divergence of A equal to 0. And even if this is 0, the remaining term, namely the gradient of 1 over c square, etc., that itself is going to make complication. We do not have a method to solve the differential equation. And therefore you ask the last question, last possibility. What is the last possibility is, why don't you make the entire quantity 0? Entire quantity 0 means what? It is, I'm asking the question, what happens if divergence of A plus 1 over c square dou phi by dou t, that entire quantity should go to 0. What is the meaning of that? The meaning is divergence of A should be equal to the negative of 1 over c square dou phi by dou t. So you are actually asking the question, do we have the freedom of setting divergence of A is equal to negative of 1 over c square into dou phi by dou t? That is a question, and you know the answer. We have seen in the lecture number 20 that we have the freedom of fixing divergence of A to any number we like. We have the freedom of fixing the divergence of A to any number we like. In the lecture number 20, we have fixed that number to 0. Okay, because at that time fixing 0 was more comfortable. Now we will fix divergence of A to be equal to negative of 1 over c square into dou phi by dou t. And if it is the case, if you are able to fix that, of course it is possible to fix like that. If you are able to fix that, then what happens is the entire term, the first term completely, the entire bracket, that term disappears or goes to 0, and we are therefore left out with the wave equation, which means that we can solve. So keeping this important discussion, I will write down the conclusion now. So what is the conclusion is that till now whatever we have done, okay, all information in the four Maxwell's equations are now extracted. It's over. All information from the four Maxwell's equations are now extracted. And where are the extracted information? They are now contained. They are now available in equation number 6 and 7. They are now available in equation number 6 and 7. Equation number 6 and 7 means what? Whatever we have just now got it, right? The one which is 7 there, and then you can always see equation number 6 that was there. This one, okay, you have this equation. So these two equations contain all information from the four Maxwell equation. So naturally one question comes. What is the question is, you have equation number 6 and 7, right? That is only two equations, but Maxwell equation is 4. How two equation will contain the information from four equations? Isn't it as if you have compressed, right? Four equation means you have a lot of information. Two equation means there should be little information, right? But now you are going to tell, what you are going to say is that all information in the four differential equations are now contained in only two equations. That means in the two equations you have a lot of information. That means it got compressed. I mean, lot of information is contained in two equation itself. And what it means is to, in mathematically, okay, mathematically what it means to say is that equation number 6 and 7 are second order differential equations, whereas the Maxwell's equations are all first order differential equations. So now you see what do you mean by compressing the information. Okay, a lot of things are put into two equation means what happened is the order of the differential equation is increased. Equation 6, 7 is second order differential equation. Maxwell equation, 4 of them are there, but all the 4 of them are first order. and therefore there is nothing to worry about. Even though two equations are there, they are second order differential equation, and therefore it contains all information that was available in the four Maxwell's equation. Okay, to see all these things in one place, let me bring the equation number 6 and 7 here so that you can see it here. Whatever equation you have, right, the two equations, I'll copy it here. Yeah, so now this, so now you will be able to see what I'm trying to say. Now you are able to see visually second order derivatives are there here. So this also is a gradient of gradient. Of course this is 0, you forget that this term is going to 0. So here you have del square, second order space derivative, second order time derivative, and here one derivative for space, one derivative for time. So ultimately all this differential equation is second order differential equation. So therefore uh, uh, of course there's nothing wrong in saying that two equation is containing all information from four equation because of this particular point. Okay, and typically we say that the price that we paid in doing this exercise is that we have increased the order of the differential equation. That is the ultimate meaning, and this particular point also I would like to write down. So this statement also I will write down, that equation number 6 and 7 are second order partial differential equation, whereas equation number 1 to 4, all the four of them are first order PDE. Okay, so which one is the potential formulation? You already know equation 6 and 7, that is the potential formulation. I'll write down that the equation corresponding to 6 and 7, they are known as the differential equation corresponding to the potential formulation, and the Maxwell equation you already know, that is the field formulation. Okay, so already coming back to the gauge, I already explained you. Do you want to choose only divergence of A equal to 0 or some other value? That is already explained. Now I will write down that if you are interested to choose divergence of A equal to 0, then what happens is you are able to solve only equation number 6. Okay, that is called Coulomb gauge if you are going to choose. So this is very clear here. So what I am trying to say is, do you want to choose divergence of A equal to 0, that is Coulomb gauge, or do you want to choose divergence of A equal to negative of 1 over c square into dou phi by dou t? That is the question. If you are going to choose Coulomb gauge, then equation 6 is fine because this goes to 0, we are very happy. But equation number 7 is troublesome equation. And therefore, we will make a conclusion that we will reject the Coulomb gauge. That means divergence of A is not 0. We don't want 0 there. Instead of 0, we will consider divergence of A equal to negative of this quantity. So that point I will now write down. So the entire quantity that you have here in the first bracket. And now ask the question that if we are going to choose, let me write down in a different color, for example, if the divergence of A, then plus 1 divided by c square dou phi by dou t is all 0, then we will give it by the name Lorentz gauge. So we ultimately we are fixing some number or some value, right? So what we are fixing is divergence of A equal to negative of 1 over c square dou phi by dou t. If you are going to fix like that, okay, then we can give this particular gauge another name, and that name is historically known as the Lorentz gauge. So if you are going to use the Lorentz gauge, then this entire term goes to 0 and we are left out with the wave equation, and therefore we are happy with the equation number 7. But that is okay. But again, you'll have to remember, there is very important point is there. What is very important point is, for equation number 6 using the Coulomb gauge, for equation number 7 using the Lorentz gauge is completely wrong. If you are going to make that kind of mixing of the gauges, then totally you are messing up everything, and any mathematics that you are going to do is completely wrong. We can't use two different gauges in the same calculation. In the same calculation, remember, equation number 6 and 7 are coupled differential equation. Coupled, right? Coupled means what? You have two unknowns here, phi and a, and here also you have the unknowns phi and a here also. Okay, but therefore what happens is there is a phi here. Remember, there is a phi here. Therefore, the phi and a is there together, and therefore coupling is there. So when coupling is there, you can't solve one equation independent of the other. You have to deal with two equations together. That is what is known as a coupled equation. So when you're dealing with two equations together, applying one gauge to one equation, second gauge to second equation will not work. And it's totally wrong. Like it is equivalent to saying, what do you mean by saying that? It is very equivalent to saying that you are going to use 1 meter as two different scales. I use two different scales of two different length and saying that for one thing I will use one length as a meter. For another work, I will take another length as a meter. Like your suppose if you are stitching a shirt and a pant, for example, when you are when you are making the measurement to stitch your shirt, I will take a particular scale. One length will be there. That's not 1 meter. Some scale I will take, and that length I will measure for taking the measurement for stitching the shirt. And for stitching the pant, I will take another scale which is of a different length and say that that is 1 meter. If you do like that, how it will entire thing will be a chaos, right? So therefore, when you are making the stitching, or when you are making the measurement for shirt and pant, you have to use the same scale in the throughout the complete stitching process. Otherwise all measurements will go wrong, and totally it will go wrong, right? So that is a kind of scenario that you'll have to imagine. And you will have to use identically same gauge. If you are going to use Coulomb gauge in 6, use the same thing in 7. If you are going to use the Lorentz gauge for 7, use the same Lorentz gauge in equation number 6. This is very important. And therefore, once you are making this kind of clarity, so let me therefore write down how we are going to deal with the Lorentz gauge. So equation 6 and 7, so whatever I explained, let me therefore write down. I put a line here. So almost everything is over. Now we would like to make this particular statement about the gauge. So you have the equation number 6 and 7 that are appearing too complicated in order to solve them. So why are you worrying about the complication? Is that we don't have a solution method. That's the reason. But now the idea is that if you are able to use, if we can use the Lorentz gauge, then we are happy. In what way we are happy is equation 7 is simplified. Equation 7, what happens? I already explained what happens. You simply delete the first term, and then if you delete the first term, and then what is remaining? Second term only is remaining. So I am writing the second term, dou square A by dou t square, which is equal to minus of the mu naught into J. That's all about it. And that will be the equation number 7. So it is the same equation. So I will try to maintain the same number. It is the same equation 7. Maybe I will say 7A. Okay. Same equation under the gauge. Okay. That's the meaning. So this is the equation number 7 under the Lorentz gauge. And what is a good thing about making use of this Lorentz gauge is that the entire equation is actually the very standard wave equation, but it is in 3 dimension, and therefore it is in vector form. Okay, which means that we have the standard methods for the solution, or we know the solution method. Okay, so that's all about the purpose of gauge transformation. And therefore I would like to say that this is the reason for using. So now you understand why we used all the gauges. So I would like to write down that this is the reason for using the gauge transformation. Okay, so that's clear. Equation number 7 is fine, but as I already told you, that what happens then to the equation number 6? I said that you have to use the same gauge, right? You have to use the same gauge for 7 and 6. So 7, the problem is clear, equation number 7. But equation number 6, what happens, we have to see. Okay, so therefore you now substitute the Lorentz gauge here. So I'm going to substitute Lorentz gauge. So what is Lorentz gauge? Divergence of A is equal to negative of the 1 over c square into dou phi by dou t. So that is your Lorentz gauge. that will be equal to minus rho by epsilon naught. So now you see that equation 6 also is under the Lorentz gauge. And if you simplify this, you get a minus 1 over c square into second order derivative in time, and you get a minus of the rho by epsilon naught. And after writing this, we are again, we are of course, it's a surprise for us. Why it is surprise is this equation is also looking like a wave equation. Exactly, this is a wave equation. This we didn't expect actually. So surprisingly, what happened ultimately, you see that if you are going to use the Lorentz gauge, all the equations have been converted to the wave equation. And this is, of course, right, this is a scalar equation, so we have only one component. And therefore, our conclusion, what is the conclusion is that, okay, we ultimately have everything in a single form, namely the wave equation, and therefore we can solve all of them. That is the conclusion. So I will write down what is the conclusion. By writing the equation, I will just copy the two equations, 6a and 7a. So once you have the 6a and 7a, which is what we have derived by making use of the Lorentz gauge, this is a single scalar equation, and this particular equation is actually set of three equations for the a vector. All of them are identically the wave equation, which means that what is the advantage is that, which means that if you know how to solve one equation, you can solve all the equations together. You don't require different methodology to solve, right? You see what is the advantage. Now what is the power of this Lorentz gauge? If you are not going to use any gauge, and if you are going to deal with the Maxwell equation, then you have different varieties of the Maxwell equation. Divergence of E equal to rho by epsilon naught is, you have a Poisson equation, and divergence of magnetic field is 0. That was a Laplace equation. Laplace equation and Poisson equation are, once again, you have to use different techniques for solving. And then coming to the inhomogeneous equation, we have the curl equations for them. And therefore the you have to apply different methods for solving the different four Maxwell's equations. But now you see, in this potential formulation, you don't have to use four different methods for solving the differential equation. You only have to know only one method, what is known as the solution to the wave equation. If you know that, all the four of them can be solved using the same method. And therefore we say, once again, this is the third advantage. We already discussed about the two advantages already. Now the one more advantage we are discovering is that we are actually making use of the knowledge about the single method, namely the wave equation solution, to learn about the potentials, that is electromagnetic potential. And once we get the potentials, we can always calculate the electric field. Now how do you do it? That's what I've written at the last. What I'm trying to say is that once we calculate phi and a, that means phi you calculate from the equation number 6, and capital A you calculate from equation number 7. And that is there is an interesting point I forgot to tell you, that the Coulomb gauge has made one more advantage to you. Okay, now I have been telling fourth advantage, right? Fifth advantage is there now. What is the advantage you're able to see is, I have been telling that the differential equations are coupled differential equation. Now you see that it is decoupled. Decoupled means the electric potential doesn't appear in equation number 7. Magnetic potential doesn't appear in equation number 6a, 7a. But you see the previous one. Previous one means before applying the gauge transformation. Before applying the gauge transformation, both equation will contain both potential. And that is what we say coupling. So coupled partial differential equation has become uncoupled differential equation. Therefore, actually, this is a really great advantage. Therefore, this particular Lorentz gauge has helped us to decouple the equations. There was a coupling, right? Now decoupling means decoupling one potential from the other potential. So you can now happily solve equation number 6a by forgetting equation number 7a. Totally you can forget and solve it, and then get the information about phi. And then once again you solve each component of the a vector separately, that is independently, and then assemble all the three of them. That will give you a vector. So once I have the information about the two potentials, namely the electromagnetic potential, we can always construct, or we can always calculate the corresponding fields using equation number 5. And of course equation number 5 Equation number 5 should be, the equation that we already started. Maybe I will show you. Yes, this is the equation number 5, right? So what is equation number 5 is, we are able to construct, or we are able to calculate the field if I substitute the, already known value for the potential, known value for the capital A vector. If you substitute them, I can now calculate electric and magnetic field. Therefore, ultimate conclusion. So what is the ultimate conclusion is that the potential formulation that we have discussed now is, now it is complete. Complete means we are able to understand the entire electromagnetism instead of Maxwell's equations. Okay, that is the point to be noted. So that is the main conclusion. I think this is the place we will stop. The point to be noted is that the entire thing is what is known as the potential formulation in electrodynamics. So make a note about this, and we can make use of this kind of a freedom. And making use of this freedom is exactly what is the uh, gauges. So probably I will stop in this particular place, and in the next class we will discuss something on the electromagnetic waves and electromagnetic energy. In the next class we will discuss that.